So 9.4, now you're doing the hypothesis test for proportion. So for proportion, z value. Okay, so these are all going to be z's. So we're going back to the z table. So let's see. We only consider proportion sampling for distributions with large samples. So we use the z distribution. Okay, so you're using the same chart for z values that you used at the beginning of chapter 8, or you can use normal CDF depending on the regions. So for example, for a two-tailed test with a significance level of 0.05, you would need to divide that into 2, which would give you 0.025 on either side of the graph. Okay, so if I plot this, I've got an area of 0.025 on the left and an area of 0.025 on the right. Okay, and then I would find the significance, or sorry, the z value for the area there. So remember to find the z value there. I don't know what just happened to my writing. There it is. Okay, find the area there. You would do inverse norm, area to the left, and then the mean and the standard deviation, in which case will be 0 and 1. Okay, so second distribution, inverse norm, our area to the left, 0.025, 0 and 1, gives us a negative 1.96. That's the value on the left, which means the value on the right is just a positive 1.96. Okay, or you could look this one up on the confidence intervals, because it is two-tailed, which would be a 95% confidence interval. Okay, and then your region in the red, anything less than negative 1.96 or greater than positive 1.96 is going to be your rejection region. And if our value falls in between, we will fail to reject. Okay, a left-tailed test with a significance level of 0.02. Okay, you have an area of 0.02. You would need the z value, so again, inverse norm. Area to the left would be 0.02. We would have a mean of 0 and a standard deviation of 1. So this would be a negative 2. This one I am going, the only reason in the first one I rounded to 1.96 was it was a common value, and also if I went to 4 decimal places, it would be 9600. Okay, this one I am going to pull out 4 decimal places because it's not a common value. So this is negative 2.0537. Okay, so that is my z value, which means my rejection region would be to the left of negative 2.0537. If I got a value greater than that, failed to reject. And then a right-tailed test for 0.025. Okay, when you're doing inverse norm, you want area to the left. So I would want the area to the left of 0.025, which would be 1 minus 0.025. So I'd put inverse norm 0.975, and then 0 and 1. Or you could do it with the 0.025. You're just going to get the negative value, and then you know that it's on the right side, so you would want to make it positive. Okay, so that is, again, 1.96. Rejection region would be to the right. Okay, so the start of all of these problems is basically the same. Biggest thing, is it a t or is it a z? And then you determine your critical value from there. All right, so we've got a problem here, 9.61. Let me see if I can pull that one over. And we do a proportion test. All right, 9 point. It's coming. Nope. There we go. Okay. So we're looking at this problem here. All right. According to a study conducted in 2015, 18%, so you're given the percent proportion, 18% of shoppers say that they prefer to buy generic instead of name brand products. Suppose that in a recent sample of 1,500 shoppers, 315 stated that they prefer to buy generic instead of name brand products. At a 5% significance level, can you conclude that the proportion of all shoppers who currently buy generic instead of name brand products is higher than 0.18? Use p-value and critical value approach. So our mean is, let's see here, I'm looking at the problem. Okay, so the mean is 18% of shoppers prefer generic instead of name brand. Okay, and then our alternative is, can you conclude that the proportion is higher, which would be to the right of 18%. So if I'm looking at this here, I have a null hypothesis that my mean is equal to 0.18 and an alternative hypothesis that my mean is greater than 0.18. Okay, then let's pull the rest of the information here. So my sample size was, from the problem, 1,500. My p, which is the mean, is 0.18. Now my p-hat, I'm not sure if you guys caught that, it wasn't actually given to us, but we were given that 315 out of 1,500 said they preferred that. So that's actually your p-hat. So you need to do that calculation, 315 out of 1,500. So let's see, that is going to be a 0.21. So your p-hat is 0.21. Okay, if my p-hat is 0.21, then my q-hat is going to be 1 minus 0.21, 0.79. Okay, so then the standard deviation of p-hat is the square root of pq over n, which means we're going to be doing this. 0.18. Our q, oh, we need the q, not the q-hat, so q, 1 minus 0.18, 0.82. Okay, then over my sample size, 1,500. Okay, so let's go ahead and do that calculation. So square root of 0.18 times 0.82 divided by 1,500. So it's going to give me 0.0099. Okay, that's going to be my standard deviation of p-hat. And then finally, the significance level was, what was the significance level here? 5%, 5% significance level. So 0.05 for my area. All right, we want to find the critical value of the test statistic. So let me pull this down here so we can look at this. The significance level was 0.05 and it is a right-tailed test. So underneath the curve, you have a 0.05. We need the z-value right here. So we want the area to the left, which would be 1 minus 0.05, so 0.95. So inverse norm, 0.95, 0, and 1. That gives us a critical value of 1.6. It's really 1.65, but 1.6449. Okay, which means my rejection region is going to be greater than this value in this red here. So we will reject if our Z value is greater than 1.6449. So just to fill in these two blanks here, the critical value is 1.6449. We get that from doing inverse norm, and then you had 0.95, 0, and 1. And then we had a right-tailed test. All right, now we need to calculate the test statistic. So we are going to do this. We are going to go a Z value, which is going to be P hat minus P over the standard deviation of P hat. So if we pull the information from the top, we've got a P hat of 0.21, a P of 0.18, and a standard deviation of P hat of 0.0099. So 0.21 minus 0.18 over 0.0099 gives us 3.0303. Okay, so my test statistic is a Z value of 3.0303, which means it goes all the way over here in my rejection region. Okay, so we compare it. We say 3.03 is greater than 1.64. So we will reject the null hypothesis, which means we have reason to conclude that more than 18% of people prefer to buy generic instead of name brand. P-value. Okay, you're going to go normal CDF. Okay, you're getting the area from here, this 3.03 to the right. So 3.0303, upper limit 99. So normal CDF, 3.0303, comma, 99. And that gives us 0.0012. And then our alpha, our significance level, was 0.05. So we compare those. We have the p-value first, then the alpha. It is less. When it is less, you reject. Okay, next problem, we have 9.62. According to the U.S. Census Bureau, in 2014, 62% of Americans age 18 and older were married. A recent sample of 2,000 Americans age 18 and older showed that 58% are married. Can you reject the null hypothesis at a 1% significance level in favor of the alternative? So they're telling you what the alternative is here, that the percentage of the current population of Americans age 18 and older who are married is lower than 62%. Okay, so we have a null hypothesis that the mean is 62%. The alternative, that it is lower than 62%. Okay, so let's get our information put in here. you've got a mean equal to 0.62, alternative that it is less than 0.62. Okay, and then the information given in the problem, we have a sample size of 2,000 Americans. A P is equal to our mean, so that is 0.62. P hat is what was given in the sample, which was 58% of them in the sample were married. And we had a 1% significance level. We'll come back to this right here. So 0.01 for our alpha. For our standard deviation of P hat, let's go ahead and do that. You have a P of 0.62. So 0.62, which means our Q is 1 minus 0.62, which is 0.38 over a sample size of 2,000, and the square root of all of that. So let's go ahead and do that. So 0.62 times 0.38 divided by 2,000. That's going to give me 0.0109. 0.010, yeah. Let me do that twice just to make sure. Square root that. Okay, good. All right, so we have everything. We need the test statistic. So let me go ahead, actually, let's go ahead and plot this, find the z-value. Let me make it a little bit smaller so we can see everything. There we go. Okay, so on my chart, let's see, you've got a significance level of 0.01. Okay, so let's get this z-value with an alpha of 0.01. So we're going to go inverse norm, 0.01, 0, and then 1. And that'll be negative 2.3263. All the way down there at the bottom, that is our test statistic. Okay, then we are doing a left-tailed test. I already wrote that down there. Sorry about that. Okay, so it's left tail because the alternative is less than, so it's pointing to the left. So whatever the way the alternative is pointing, that is how we will do our test, which means our rejection region is to the left of negative 2.3263. So we will reject if our z-value is less than negative 2.3263. So now we're going to calculate this. So we're going to do z equals p hat minus p over the standard deviation of p hat. Okay, based on this data here. So our p hat is, let's see, 0.58, our p 0.62, our standard deviation of p hat 0.0109. So 0.58 minus 0.62 divided by 0.0109. So negative 3.67. That is our test statistic. And if we put that on the chart, you can obviously see that that is less than negative 2, sorry. So we say negative 3.67 is less than negative 2.3263. So we will reject the null. Okay, which means we have significant evidence to conclude that the alternative is true. So let's do the p-value approach real quick. All right, so the p-value approach, we would need to find the area, okay, or the probability of negative 3.67. It's to the left, so your lower limit will be going to the left, so that'll be negative 99. So we'll do normal CDF, negative 99, negative 3.67. And that should be close to 0 again. We get three zeros and a 1, so 0.0001. Compare that to the alpha, which was 0.01. It is less than alpha, you reject. All right, the next problem I have is rejecting again. I want to find one where we do a fail to reject. So give me a second here. Okay, so let's do what happened to the problem I just had up? Hold on. Okay, so the problem is 9.76 in the book. All right, so customers often complain about long wait times at restaurants before the food is served. A restaurant claims that it serves food to its customers on average within 15 minutes after the order is placed. A local newspaper journalist wanted to check if the restaurant's claim is true. A sample of 36 customers showed that the mean time taken to serve food to them was 15.75 minutes, with a standard deviation of 2.4 minutes. Using the sample mean, the journalist says the restaurant's claim is false. Do you think the journalist's conclusion is fair to the restaurant? Use a 1% significance level to answer this question. Okay, so first of all, this is a t distribution. Okay, we know it's a t distribution because we are not given a population mean. We're just said it's within 15 minutes. Okay, we are given a sample mean, so we are using a t distribution. So let's write down the information that we have here. So we have to kind of cross out some of this stuff here. So this is 9.71. Okay, we have a sample size was 36. I lost the problem again when I moved it over. There it is. Okay, 9.76. All right, so we have a sample size of 36 customers. Okay, we don't have a p, we have a mean. Okay, so just change that to a mu. Okay, you did have that the restaurant claimed it was within 15 minutes. You do have a sample mean, okay, within the 36, so that's x bar, of 15.75 minutes, with a sample standard deviation of 2.4 minutes. We want a significance level of 0.01. All right, so the restaurant claims that the orders are 15 minutes or within 15 minutes. So basically less than or equal to 15 minutes. The alternative hypothesis then, what the journalist is testing, is that the mean is greater than 15 minutes. So when we look at our normal curve, we want a significance level on the right tail because of the alternative is that it is greater than 15 minutes. So this is a right tail t-test with a significance level of 0.01. So on my curve, I have 0.01. I would want the t-value for that. So the degrees of freedom would be 36 minus 1, so 35. So if I look up my significance level here, let's see here, 36 customers. So 35 for the degrees of freedom, so this last row here, 0.01 gives us a 2.438. Okay, so that is our t value here, 2.438. So we're going to run the test, and we're going to say that we're going to reject if we get a value greater than 2.438. So our test statistic, 2.438, we will reject if we get a value greater than 2.438. Okay, so to calculate the test statistic, we want to do x bar minus the mean over the standard deviation of x bar. Before we do that, we have to find the standard deviation of x bar, which is the standard deviation of the sample over the square root of the sample size. So the standard deviation of the sample is 2.4. The square root of the sample size is 36. So we're going to do 2.4 divided by the square root of 36. We're going to get 0.4. Okay, then we're going to do our t value. So that's going to be x bar 15.575. Sorry, just 15.75 minus 15 over the standard deviation of x bar, 0.4. So let's go ahead and get that. And that's going to give us 1.875. So my test statistic, 1.875. So if I chart that on my graph here, that is going to be about right here. So this is not in my rejection region. This is in my region with my smiley face. Okay, so we say that 1.875 is actually less than 2.438. So we say fail to reject the null. Okay, so in that case, we fail to reject. So we say the mean we have significant evidence that the mean is correct here. Okay, that we get orders out within 15 minutes. So you would say here the journalist's conclusion is not fair to the restaurant based on this information here, a 1% significance level. Basically, 99% of the time, okay, the orders are coming out within the mean. P-value approach, okay, find the p-value of 1.875. So it's on the right of the mean. So you would do 1.875 to 99. So we would go normal CDF with a lower limit of 1.875, an upper limit of 99. So second distribution, 1.875, 99. So that gives us 0.0303. Okay, then we have compared to the significance, 0.01, it is greater. So when P is greater than alpha, then you fail to reject. P is less, you reject. P is greater, fail to reject. All right, you guys want to do one more? No? We're doing one more. I'm going to find one though, hold on.